You've probably heard this one before, right? Maybe in a sci-fi movie or a physics class. The faster you go, the heavier you get. It's one of the most famous takeaways from Einstein's theory of relativity. But, is that really the whole story? Well, as we're about to find out, the real answer is so much cooler. Let's get into it.
So let's just ask it straight up, does it? Well, the short answer is, yeah, kind of, but absolutely not in the way you're probably thinking. The real story here is way more interesting. It's this incredible tale about a major crisis in physics, a totally brilliant solution, and an idea so powerful it helped us build our entire modern view of the universe, only to be, well, gracefully retired by the very people who came up with it.
To get what's going on, we have to rewind the clock to the late 1800s. See, physics was built on these two giant pillars, and the problem was they were starting to contradict each other. On one side, you had Newtonian mechanics, the stuff that had been working perfectly for 2 centuries. In Newton's world, mass is just mass, and if you're moving and you throw something, the speeds just add up. Simple. But then you had Maxwell's theory of electromagnetism, which was this beautiful description of light, and it predicted something totally bizarre. The speed of light is always the same for everyone, no matter what. You simply couldn't have both be true at the same time.
And look, this wasn't just some small disagreement. This was a full-blown crisis. It put the 2 most successful theories in the history of science on a direct collision course. Physics was, for all intents and purposes, stuck.
This little train thought experiment just nails the problem perfectly. The first part makes total sense, right? You're on a train going 50, you throw a ball at 20, the ball's going 70 relative to the ground. Easy. But here's the kicker. According to Maxwell, if you're on that same train and you flick on a flashlight, the beam of light doesn't move at your speed plus the speed of light. Someone on the ground sees that light moving at the exact same speed you do. See, it just completely broke all the common sense rules of motion, and it created a paradox that had physicists totally stumped.
And then, of course, in 1905, a young Albert Einstein shows up. But what he did wasn't what you might expect. He didn't just tear everything down. In a funny way, his move was actually deeply conservative. It was all designed to save one of the most sacred fundamental laws in all of physics, the conservation of momentum.
He started with just 2 really simple but incredibly powerful ideas. First, he said the laws of physics have to be the same for everybody who's moving at a constant speed. That seems fair. Second, he just took Maxwell's weird prediction and said, okay, that's a fact. The speed of light is a universal constant, period. And with those 2 things as his foundation, he decided to see what kind of physics you'd build on top of them.
Now, all the wild consequences of these ideas, they get captured in this one elegant little piece of math, the Lorentz factor. We use the Greek letter gamma to represent it. And honestly, this little equation is the engine of special relativity. It's the magic number that tells you precisely how much your measurements of time, space, and yes, mass get warped as your velocity v gets closer and closer to c, the speed of light.
So this leads to this really amazing chain of logic. The moment you accept Einstein's 2 postulates, you find out that the old trusty formula for momentum, P equals mv, it just doesn't work anymore in every situation. So rather than ditching the whole idea of conservation of momentum, which would have been huge, Einstein tweaked the definition. He added that little gamma factor. And this is the clever part. Physicists realized they could look at this new formula, P equals gamma mv, and interpret it in a new way. It was still P equals mv. You just had to think of the m as this new, changing quantity.
And boom, just like that, the whole concept of relativistic mass was born. So what is it? It's not really the amount of stuff an object is made of. It's its effective inertia, how much it resists being pushed, that an observer measures for an object that's moving. And here's the most important part. Its value totally depends on your perspective, on who's doing the measuring.
Okay, so this brings us right to the heart of the matter. To really get this, you have to understand that relativity basically created a tale of 2 different kinds of mass.
On the other side of the coin, we have what physicists today just call mass. That's it. Its fancy name is invariant mass, or rest mass. This is the mass an object has when it's not moving relative to you. It's a fundamental, intrinsic property of the object, kind of like its electric charge. It is constant. It never, ever changes. Every single person in the universe will agree on its value, no matter how fast they're flying around.
So let's put them side by side. Relativistic mass? It depends on who's looking. Invariant mass? It's absolute. Relativistic mass? It's an idea that's pretty much been retired by professional physicists. Invariant mass? That's the gold standard. And this really gets to the core of it. Relativistic mass is really just another way of talking about an object's total energy. Invariant mass is a fundamental property of the thing itself.
But here's the thing. Even though the idea of relativistic mass is retired, it has some absolutely incredible consequences. For one, it gives us a really intuitive way to understand why there's a cosmic speed limit.
Knowing this actually gives us a much richer way to look at the most famous equation in the world, E = mc squared. You can actually read it in two different ways. If you use m for relativistic mass, the equation tells you the total energy of a moving object. That's its rest energy plus its motion energy. But if you use m for the invariant or rest mass, it describes the absolutely staggering amount of energy that's locked up inside an object even when it's sitting perfectly still.
And we can get particles moving insanely fast. I mean, at the Large Hadron Collider, they accelerate protons to this speed, 99.9999991% of the speed of light. That is just mind-bogglingly close. But here's the thing. They can never, ever get it to 100%, so why not?
Well, let's look at what happens to that gamma factor, which is really just the relativistic mass. At half the speed of light, an object's resistance to acceleration has only gone up by about 15%. No big deal. At 90%, it's more than doubled. But look at 99.9%. It's now over 22 times harder to push. You can see the curve just skyrockets. You're hitting a wall. And that steepening curve points to the ultimate barrier. As you get infinitesimally close to the speed of light, an object's relativistic mass, its inertia, balloons towards infinity. And to push an infinitely massive object any faster, well, you'd need an infinite amount of energy. And since there isn't an infinite amount of energy lying around, nothing with mass can ever, ever reach the speed of light. It's the ultimate, unbreakable speed limit of the cosmos.
So, if this idea is so powerful, so intuitive for explaining the cosmic speed limit, why on earth did physicists get rid of it? And that brings us to the final chapter in our story, the legacy of this brilliant but retired idea.
The reasons are both practical and, you could say, philosophical. For one, it's just redundant. Relativistic mass is really just total energy in disguise, so why have two names for the exact same concept? It's also really confusing. It makes people think an object is somehow gaining more stuff as it speeds up, which just isn't what's happening. And honestly, it's just not as elegant or as powerful as the modern way of thinking, where energy and momentum do all the dynamic changing, and mass is just this one solid, unchanging property. And you know who became one of the biggest critics of the idea? The man himself. In his later years, Einstein really came to dislike the concept of relativistic mass. He argued that it was just clearer and better for physics to only ever talk about one kind of mass, the rest mass.
So if there's one thing to take away from all this, it's that relativistic mass was never wrong. Not at all. It was a perfectly good description of a real physical thing. But science is always sharpening its tools, refining its language. Think of relativistic mass as a kind of conceptual scaffolding. It was absolutely essential for building the incredible structure of modern physics. But once the building was up, the scaffold could be taken away, revealing the more fundamental, more beautiful reality underneath.
And that kind of leaves us with a final thought to chew on, doesn't it? What essential scaffolds are we using in science right now? What are the ideas we lean on every day that are super useful, but might, one day, just be seen as clever stepping stones on the path to an even deeper, more elegant truth about our universe? Thanks for joining me for this explainer.